All right. Any questions that you may have? No question? Other than that, life is comfortable? Very comfortable? Okay. Huh? You have a question?
Yep.
So life is not comfortable. Okay.
Hey, will you post the homework one solution on the...
I already posted.
But that's not the homework we have.
Did you look at the web?
Yeah, I did.
I don't think so. You look at the web.
You updated that?
Huh?
You have updated the homework.
It's updated.
Sorry.
It's updated. You didn't look at it. Okay. So now the life is comfortable. Okay. Any other question? Any other question? All right. So let's keep on going. And so last time we discussed about the kinetics of the particle. And we said that basically you identify the forces that happen into the particle. You identify all of the forces, F1, F2, F3. And as a result of that, when this particle obtains some inertia, mass times acceleration. And you can do anything. Whatever you do to this picture, you do to this picture. So that is basically, these are called equivalent system. Equivalent system. So let's go ahead and do one problem and using this concept. And of course, we are doing the particle. And hopefully, maybe today I do for rigid body. And you can also develop the equation motion. Equation motion. Let's start with a simple problem using this concept. And then I do other thing. And everything comes from F is equal ma. But maybe different version of it. So let's talk about the problem. Let's talk about simple pendulum. Simple pendulum that you have. Mass m. Gravity is acting. And this is a simple pendulum. Length L. And maybe this is subject to a force F of t. And this angle is a theta. And theta is evolving as a function of time. And you can say, what is the equation motion? So you can say, no problem. First, I have to find acceleration of this one. And acceleration of this particle is a cylindrical coordinate system is r double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta. And of course, you do not have this. You do not have this. The only thing that you have acceleration is minus L theta dot square ER. And of course, ER is here. And E theta is in this direction. Plus L theta double dot E theta. So you can say that my free body diagram is mg. I have a tension T that is internal, and I have a force F of t, which is here. And as a result of this, all of these things, my particle obtains some inertia, and I have mass times L theta double dot and mass times L theta dot square. So whatever you do to this picture, you do to this picture. So if you take the summation moment with respect to point A for this picture, you can write summation forces in x direction for this picture must be equal to summation forces in x for this picture. Summation forces in y direction for this picture must be equal to summation moment for this picture. You can do anything you do to this picture, you do to this one. So and if you take the moment with respect to point A for this picture, this internal force T get eliminated. So you can say mg times this distance, L sine theta, and that's a clockwise, minus ft times L, that's counterclockwise, is equal to minus ml square theta double dot. So your equation of motion becomes ml square theta double dot plus mgl sine theta is equal to f of t. Very simple equation. So we also solved a problem in the class before. We said that you do have a bar here, and we do have another bar that's coming here, and the length of this one is 0.4 meter, and then it comes down 0.1 meter, and then it goes down here another 0.1 meter. Well, no, I think here 0.4 meter. Then you do have something that is rotating here. So you do have another arm that's going up here. Maybe there is a motor here that rotates this one. And that goes 0.2 meter. And then it comes down. And then it goes like this. And you can think about it like this mechanism. And you're holding a marble here. And this distance from here to here is 0.1 meter. That's 0.2 meter. This one is also 0.1 meter. So you are holding an object like a jaw. And so you are holding this piece, and we are assuming it's a particle. Next time we solve this one if it's a rigid body. So, and hopefully maybe we can start that one today. So now you do have this, and this whole system is rotating around this one with omega 1 equal to 0.2 radian per second, and omega dot 1 equal to 0.1 radian per second square. And this one is rotating respect to this arm, with omega 2 0.4 radian per second, and omega dot 2 equal to 0.3 radian per second. So this is rotating relative to this. This is relative. Relative to this arm is rotating. It's very hard to say relative to the ground because then you have to know what angle you are talking about. So it's very hard to get. This one is relative. So if you have XY coordinate system attached to here, it is rotating respect to this one. The angle is changing in the plane of the X and Z. So it's very easy to monitor the rotation. And this one is rotating respect to the ground. And of course, if you are holding this piece with some jaw, you have applied certain force to this particle to hold it. Otherwise, the particle will fly. So you may be interested, some force is happening to this one. You said, no problem. The first thing that I have to find, what is acceleration of this particle. And to obtain acceleration, you need auxiliary reference coordinate system. You can put the main reference frame here, and then you do have auxiliary reference coordinate system. This auxiliary is attached to here. This one is rotating respect to auxiliary. So now you can say velocity of the P is equal to I have to go on up. Velocity of point P is equal to velocity of the R dot O, which I can call this point O, plus Vxyz plus omega, that this auxiliary reference frame is being rotated, time rho xyz. And at this instance, r dot O at this point, it simply is going around the circle, and it's going out of the page, and this is your x, and it's going into the page, and that is basically omega 1 times 0.2 radian, r omega. So r dot O is 0.4 times 0.2, and the direction is negative I. We can call it capital I, so you can say that it's in the direction of capital I. This is capital I, this is capital J, this is capital K, this is a small I, this is a small j, this is small k. At this instance, they are coincident. So this becomes equal to 0.08 capital I. Vxyz, just forget about all of these things. Forget about all of these things. And this was an exam problem, I guess, at some point I gave. And this is rotating, again, like this, with angular velocity omega 2. And it is going around the circle, and the radius is 0.1 meter. And again, it's going into the page. It's going to the page. And Vxyz is equal to 0.1 times omega 2. And omega 2 is 0.4. And the direction of that one is a negative I. But at this instance, a small I and capital I in the same direction. At other instance, no. They are not in the same direction, because this xyz is going around the circle. But this Vxyz is always in the direction of a small I. No matter what a small xyz here is, this is always in the direction of a small I, because that is what is going into the page and in that direction. So that becomes equal, Vxyz becomes equal to minus 0.04 I. Omega times rho xyz become, know that auxiliary reference frame is being twisted by this omega 1 capital K, and rho xyz is equal from here to here. That should be equal to minus 0.3 j minus 0.3 j, a small j. So this minus 0.3 j, and minus 2 minus 0.1, a small k. And omega 1 is equal to 0.2 radian per second. So this is a 0.2. So if you multiply this one, this becomes equal to k times k. Forget about it. K times j becomes negative I, and that becomes plus. That becomes plus 0.06 I. It's k times j, it's
Minus 0.3 j.
that should be plus point. So if you add all of these things together, velocity with respect to main reference frame becomes equal to minus 0.18 capital I at this instance. Of course, that's not what we are interested, but for acceleration, we may have to do some of these things, so you have to have in a background. And because we have put everything in terms of the meter and second, so this is a meter per second. You better write your unit. Make sure in your exam you write the unit as well. Now, if you want acceleration, you can say, let me erase this one. Let me erase this one. We keep this one. So acceleration to respect to main reference frame is equal R double dot O plus AXYZ plus 2 omega times VXYZ plus omega dot times rho XYZ plus omega times omega times rho XYZ. We derived this equation for you. Now we implement it. R double dot O is simply acceleration of this point, and this point has two acceleration. One is a normal acceleration, one is tangential acceleration. Your normal acceleration is going to be in this direction, your tangential acceleration would be in this direction, and that's your acceleration. And this acceleration is r theta dot square, and this is r theta double dot. Your r is 0.4, so you do have 0.4 r, I write it here, r theta double dot er, r theta dot square er, plus r theta double dot e theta. You understand that? We have done so many of these things, so I don't need to go to this detail. So you have one acceleration here, which is minus 0.4 theta dot square, and theta dot square is omega 1. That's 0.42 square. And the direction of that one is J, capital J. And you do have one in the direction of, in this direction, normal to the blackboard, and that is in the direction of the negative I. So that's r theta double dot, that is 0.4. Theta double dot is 0.1, and the direction of is I. So this number becomes equal to minus 0.016 capital J minus 0.04 capital I meter per second square. Your AXYZ, again, you do have two acceleration. One is in this direction, which is a normal acceleration. One is in this direction, tangential acceleration. It goes around the circle. So your normal acceleration would be 0.1 r theta omega number 1 square, or omega number 2 square, and the direction of k. So that would be 0.1. Omega, this one, is 0.4 square. And the direction of that one is a small k, but at this instance is the same as k. And then you do have one is in this direction, which is r theta double dot, which would be minus 0.1 theta double dot. Theta double dot is omega dot 2, 0.3. And the direction of that one is a small I, but at this instance is the same as capital I. So this number becomes equal to 0.06016 capital K and minus 0.03 I. At this instance, capital K and a small k is the same. Then you do have 2 omega times Vxyz, and our Vxyz is here, so minus 0.4 I. So I'm going to erase this one, but remember Vxyz is a point. I write it here in the bottom. Vxyz, for my own reference, is minus 0.04 I. Then I have 2 omega times Vxyz. And this is omega, but then my auxiliary reference frame is being twisted. And that's omega 1 is 2 times 0.2 k, Vxyz minus 0.04, a small I, and k times I is a j, and this number becomes equal to minus 0.016 j. Then we do have another term, omega dot times rho xyz, and that is omega dot, your auxiliary reference frame is being twisted. Your omega dot is equal to 0.1 radian per second k, and rho xyz is this number again, which is equal to is a 0.3 j minus 0.1 k, 0.3 j, a small j, minus 0.1, a small k. At this instant, j and k is the same direction, so no problem. And that becomes equal to k times k. Forget about it. K times j is negative I, so that becomes 0.03 I. Finally, we have omega times rho xyz, and that becomes equal to omega times rho xyz, and that becomes equal to 0.2k times 0.2k times 0.3j minus 0.1k. So if you multiply these things, according to my calculation, this becomes equal to k times k. Forget about it. K times j become negative I, and k times I become j. So this becomes negative 0.012 j. So k times k, forget about k times j becomes negative I, and k times I becomes j. So if you put them together, you should be able to find what is the acceleration of the particle. So no acceleration of particle respect to main reference frame. Newton's law is always applied respect to main reference frame, is going to be equal to 0.016 j minus 0.04 I, then you do have this term, which is 0.016k minus 0.03 I. Then you do have this term, which is 0.016 j. Then you do have this term, which is 0.03 I. And then you do have minus 0.012 j. So if you put them together, acceleration of the particle axyz of the particle, all of the I, you put them together, this is a 0.04 I, that becomes 0.07, and this becomes 0.1, so that becomes, all of them are negative, so that becomes 0.1. All of the j, you put them together, that's 0.016 here, another 0.016 here, and another 0.12 here. So that becomes 0.2. So that becomes, according to my note, let me see, 0.016 0.016, and all of them are negative, actually. All of them are negative. So according to my note, this becomes minus 0.044 J. And finally, you do have K, which is 0.016 K. So that's your acceleration. And if the mass of this particle, we have given the mass of this particle is 1 kilogram, mass of the particle is equal to 1 kilogram. Now you make a free body diagram, and you can say that to this particle, you have a force in the x direction, Fx, Fy, Fz. To this particle, you do have mass times acceleration in the x direction. Mass is equal to 1 kilogram, and acceleration is 0.1, minus 0.1. Mass is equal to 1 kilogram, acceleration is minus 0.004. One kilogram times 0.016. What else? What else? You also have gravity, that you forgot about that one. You also have gravity, mg, which is 1 kilogram times 9.8 in this direction. So all of those forces happening to the system. So the jar is putting some Fz, some F1, some F, and you have also gravity. As a result of all of these forces, mass times acceleration. So therefore, you should be able to say, what is Fx? So Fx must be equal to minus 0.1 Newton. Fy must be equal to 0.044 Newton. Fz minus 9.8 must be equal to 1 kilogram times 0.016. So you have all of the forces that happen into this particle. And you want to make sure your particle is not going to crush. So very simple problem. But first you have to use those auxiliary coordinate system to find all of the numbers, and then you put in your. Most of the problem that I solved is I solve parametrically. I don't want to solve numbers. You can simply substitute the number yourself. I should say this is A, this is B, this is C, and just go based on that one and find the number. But in this problem, I put numerically. So, but most of the problem I like to solve, I solve parametrically. You can put the number yourself. Any question on this problem? All right. So last time we also discussed about everything comes from the Newton's law, although maybe different version of Newton's law. And we said that F is equal to mass times acceleration, and you can say mass times dv dt, or you can say d over dt of mv, and this is called linear momentum, the change of linear momentum. mv is called linear momentum. Linear momentum. If you multiply both sides of the equation by change of position, so your force is here, and next time your system has displaced dr, this is r1, this is r2, then as you see, as a result of these forces that you have to system, your system has done some work. Force times the displacement is a work, FdR. So if you multiply both sides of the equation by FdR, this becomes work. And if you multiply this side of the equation by dr also, then you can say this is a work that has been done by the system. And integration of both sides, you can say that from a stage 1 to a stage 2, you can find what's the velocity. So if you integrate this one from a stage 1 to a stage 2, that becomes integration 1 to 2 FdR is equal to this dr dt become velocity. And this velocity and this velocity are in the same direction. They are in the same direction. So therefore, the dot product that you have, you can simply say is mv square type situation. So you can say this is equal to d over dt of 1/2 mv square. Because the product, if you make a differentiation of this one, this should be v d over dt of mv. That's the same thing. So that's basically like x squared. So that if you would like to differentiate, that would be kind of the same. So you can say this becomes equal to d over d 1/2 mv squared. And if you integrate this one, this becomes work, and this becomes kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared. We said most of the force, the work depends on the path. But if there are some forces that are conservative that does not depend on the path from a stage 1 to a stage 2, friction depends on the path. If you go from here to here, it depends on the path. But certain things like gravity does not depend on the path. And you can say why. You can say why. For example, if you do have mg here, and this displays here dr, and you can see that dr has component dx here, or dy here, and dz here. And FdR, they are in the opposite direction. Dy doesn't make any difference. dz is the one that makes a difference. So the dot product, or f times dr, becomes mg minus mg dz. Minus mg dz. And if you integrate this one from a stage 1 to a stage 2, this becomes minus mgz at 2 minus plus mgz at 1. So now you see that doesn't depend on the path. The gravity does not depend on the path, because your dr, which you go here, doesn't make any matter how you get to the dr. How you get to the dr. dr has component dz and dx. And fdr becomes basically the final location. So if the force is conservative, we said that this portion, you can call it minus v2 plus v1. Plus the force of the non-conservative from 1 to 2 fdr is equal to 1/2 mv2. And this one we can call it kinetic energy at stage 2, kinetic energy at stage 1. That would be T2 minus T1. Or you can say T1 plus V1 plus integration 1 to 2 FdR is equal to T2 plus V2. And for the case of the gravity, potential energy is mg. Potential energy is mg times z, or mg times h, the height of that from xy plane. You can also show this one also true for the case of a spring. If you do have a linear spring, you can say potential energy of linear spring is 1/2 k delta square, and doesn't depend on the path. And last time we solved a problem for you using the concept of kinetic energy. This kinetic energy really came from Newton's law. You don't have to use this concept. You can apply the Newton's law and you do the problem. Let's do some simple problem. Then you will understand what I'm talking about. So let's say that you do have a pendulum here. Pendulum here. And this pendulum is released from this position, and it comes to the final position, which is here. And this is L, and that's gravity is acting. And I ask you, what is angular velocity when it comes to this position? What's the angular velocity? So you can say, no problem. This is like a stage 1, a stage 2, and this is like a work that is done. And I'm not interested in what is happening in between. And so I simply use the concept of energy, and I can say T1 plus V1. And I do not have any non-conservative forces. Must be equal to T2 plus V2. So now you said, OK, T1 is 1/2. T1 is equal to 0. At a stage 1. V1 at a stage 1 is mg times L, respect to this reference line. T2 is equal 1/2 mass, and velocity is r omega, L theta dot. And that's angular velocity that he's asking, L theta dot, r omega square, and potential energy is 0. So from here, you can see your theta dot angular velocity becomes equal to a square root of mg, m and m cancel actually, and g over 2g over L. 2g over L. Now, suppose I don't want to use concept of kinetic energy. So I want to use this Newton's law, and hopefully when it gets to this position, I come with the same equation. So you can say, no problem. If I write equation motion for any position, theta as a function of time, or you can say this theta as a function of time. Theta is increasing. We better write theta is increasing. And this is my free body diagram, mg. That's a tension T. And as a result of that one, this obtains mass times acceleration in this direction, ml theta dot square. And it obtains acceleration in this direction, ml theta double dot. So that is basically your, and whatever you do to this picture, you do to this picture. If I take the moment respect to point, this point, and I do the same thing respect to the same point here, I have my equation motion. My equation motion becomes, let's say, take the clockwise positive, minus mg plus mg L sine theta is equal to ml square theta double dot. So your equation motion becomes equal to theta double dot minus g over L sine theta equal to 0. That's your equation. That's your equation motion. solution to this differential equation will tell you everything. How is the theta is evolving, how is the theta dot evolving as a function of theta. So this is simple differential equation, and you can say, and I'm interested in this angular velocity. How is my angular velocity is evolving? So you can say, no problem. My differential equation is theta double dot minus g over L sine theta equal to 0. And this is d over dt of theta dot minus g over L sine theta equal to 0. Or you can do the change of variable, and you can say d over d theta, theta dot, d theta dt, that's the same thing, is equal to minus g over L sine theta equal to 0. And this becomes theta dot, so this becomes theta dot, d theta is equal g over L sine theta. So this differential equation, you can solve it, and it gives you what's the angular velocity at any time. So this becomes theta dot square over 2 is equal to minus g over L cosine theta plus a constant C1. And of course, when the theta is equal to 0, you do not have any angular velocity. So C must be equal to g over L. C must be equal to g over L. So at time equal to 0, at theta equal to 0, theta dot is equal to 0. So you can solve this differential equation, and C1 becomes equal to g over L. So your angular velocity at any time become minus g over L cosine theta plus g over L. That's angular velocity at any time, how it is evolving. You don't need to use energy method. Energy method is simpler because you just look at one point, next point. In between, you don't care. But if you want in between everything, your best shot to solve by differential equation, solve the differential equation, and see what is everything is evolving. So if now you are interested when it is at a pi over 2, you simply put pi over 2 here, and you can find what's the angular velocity when the system comes to the vertical position. So you can say that system comes vertical position at theta equal to pi over 2. Your theta dot square over 2 becomes g over L, and theta dot becomes equal to a square root of 2g over L. Same answer. Same answer. All right. Now we go to another concept, and we define the concept of angular momentum. Again, looks different, but is all Newton's law. So what we had here, we had a particle subject to all of these forces. And that's equal to mass times acceleration d over dt of mv. That's called change of momentum. So last time we multiplied this one by dr. Now we can take the moment respect to any point. So we can take the moment of everything respect to this point, r. So that means that what you have f is equal to d over dt of mv. Now if I multiply both sides of this equation by r, That is like a moment. R is not the different equation, R. And that shows that moment of all forces respect to a fixed point is equal to, now this R, we can say we can take it inside. We can take it inside, and we can prove why if we take it inside there is no problem. Why it is not a problem? We can say that this is d over dt of R times mv. And the reason is that if you expand this one, that would be dr dt times mv plus R times d over dt of mv. This is what you had. This is additional term that you get by putting that R inside. But this additional term, dr dt, is a velocity, and this velocity and this velocity in the same direction, and the cross product would be 0. So this does not produce any contribution by taking R inside. So this would be 0. Doesn't produce any problem. Theoretically, you cannot take R inside, but for this application, you can take R inside for this particular problem. But otherwise, you cannot take R inside. But for this, you can take the R inside, not a problem. And you can say that I can take the R inside without any penalty. Otherwise, you have to subtract something. And this term is a moment of momentum. Moment of momentum. And sometimes it is referred as angular momentum. Angular momentum. So if you look at it, they all came from Newton's law. There is no reason to use this equation. You can always use, and you can say moment of all forces respect to fixed point is equal to the change of momentum, and sometimes we refer the angular momentum as h. This one we refer as h, angular momentum. So this looks like different equation, but is really same as Newton law. It's the same as Newton law, except this one, it looks different, like energy method. So for the pendulum that we just discussed, we may want to use this concept. Moment of all forces respect to a fixed point is equal to the change of momentum. So we can say, OK, this is my particle, mg. Moment of all external forces respect to here, that's mg times L sine theta. mg times L sine theta. mg times L sine theta. That's a moment of all forces respect to fixed point is equal to change of momentum d over dt of momentum R times mv. Your R is LER. Your velocity is in this direction. Let's call theta here. Well, in that case, if I theta here, then let's say velocity is going up. So velocity is going up. We would have to be in the direction of L theta dot E theta. We have to always go in the direction of increase in the theta. So mg times L sine theta, and clockwise positive, clockwise. Or you can say this becomes minus k. Maybe it goes minus k. So you better say k minus. It goes into the blackboard. This is x, y, and z is coming here. And mg times L sine theta. Your thumb is going to the blackboard, minus mgk. And that's going to be d over dt of momentum. And that momentum is LER times mv. And mv is ml theta dot e theta. So from here, you can say that ER times E theta is a positive K. So that becomes ML square theta dot K. And K direction never change. So therefore, the minus mg L sine theta is equal ML square theta double dot. And that is an equation motion. That's equation motion that you can do whatever you want with it. So there's another way to do the problem. So we defined moment of momentum as R times mv, and moment of all forces with respect to fixed point is equal d over dt of h. H is a vector. So as m is a vector. Nothing is scalar. In this course, nothing is scalar. Now, let's expand this one to the impulse and momentum. Let's expand this one to impulse and momentum. So again, you do have F is equal to d over dt of mv. That's Newton's law. Newton's law. You can always solve every problem with the Newton's law. But sometimes, if they are just interested at this position, the time has passed, or the delta R has passed, then you may want to use energy. But there is no reason to use energy, because energy came from the Newton's law. Angular momentum came from Newton's law. Moment is equal change of angular momentum. It came from Newton's law. Everything came Newton's law. So that's a master equation. It looks different, but it's really. So it's the same thing for here. This is Newton's law. I can multiply this both sides by dt. F dt. That's called impulse. And if I multiply both sides, it's called dmv. So if I integrate this one, that means integration 1 to 2 f dt is equal to mv2 minus mv1. That's called impulse and momentum, change of. Let's give you one example, although I haven't really worked out. As you see, when I'm solving problem, I just pop in problem. I don't look at my notes. So I just pop in a problem in my brain, and I just put it. So what I was thinking about this problem, and maybe I solve first another problem. First I solve another problem. So let's say that you do have a particle here, and this particle is going with a velocity va. Then you do have another particle here. It goes with a velocity vb. Maybe vb is smaller than va, or maybe it's coming in the opposite direction. Let's call it opposite direction, vb. Or maybe it is coming at some angle. Maybe even make it more interesting. This is going in the x direction, and another particle is coming in this direction at a 30-degree angle, like this, and it's going in this direction with the velocity vb. And they collide. And the duration of impact is delta t. And let's say the mass of this one is 2 kilogram. The mass of this one is 3 kilogram. Velocity of this one is 10 meters per second. Velocity of this one, let's say, is 20 meters per second. We would like to know that after the impact, where are the velocity and what are the direction? After the impact, what is the velocity after the impact? What are the velocity? Let me see whether I brought my calculator. No, I didn't bring my calculator, so hopefully we can solve it together. What are the velocity? Get your calculator. And direction. Let me tell you one thing before we go further. We just solved for the case of the impulse and momentum, and we said integration 1 to 2 f dt is equal to change of momentum. You can represent this equation graphically. You can represent this equation graphically. This becomes f dt at stage 2 minus f dt at stage 1 is equal to the mv2 minus mv1. So that means that if you do have integration 1 to 2 and f is constant, then you can say that, and if I have a time, you can say time t1, t2, or delta t, f delta t. Or this is f delta t. F delta t is equal to mv2 minus mv1. Or you can say that momentum plus f delta t is equal to the momentum. So you can make a picture. What is the momentum before? What is the impulse? F delta t is equal to the momentum. So you can make a picture like what we have been doing for the case of the Newton's law and say that, okay, what do I have? What do I have? And you can say, I have some momentum is coming, some impulses happen, is equal momentum. Newton's law. Newton's law. This is f delta t is equal momentum. Then we said momentum plus impulse must be equal momentum. It came from Newton's law. It looks different, but it's Newton's law. And you can make a graphical picture like this. Momentum plus impulse is equal momentum. Let's apply this picture to our problem. Let's apply this picture to our problem. Then hopefully you will understand what direction the ball are moving and what velocity they obtain after the impact. All right? So let's apply when the collision happens, there are some forces transmitted here. We can call that force F. F. So to the particle number 1, what is my momentum? My momentum was in this direction, and that's 2 kilogram times 10 meters per second. So that's 20, and the unit of that one is a kilogram times meter per second, and we can convert it to the Newton per second. F is equal to F delta t is equal to mv. F is a Newton second. Newton second is a unit. Newton second. So the unit of this one is a Newton second. You can convert it to Newton second. The unit is Newton second. Okay? Then there is some impulse has happened to this one. And impulse is normal to the face, F delta t. F delta t. And as a result of this one, the system obtained new momentum. New momentum. And what is that new momentum? What's that new momentum? It obtained new momentum. What do you say? It obtained new momentum. So momentum, impulse, momentum. What's a momentum when it obtained? Come on, guys. This is a graduate course. It's not undergraduate that I should tell everything. So what's a momentum? What's a momentum? Huh? That obtained new momentum, 2 kilogram times VA at x direction, 2 kilogram times VA in the y direction. That's a momentum. And if you know the VAX, VAY, then you are all set. Okay? That is a new momentum. For the particle B, for particle B, this is a particle B, and particle B is going with a momentum in this direction, and that is equal to 3 kilogram times 20 meters per second, 2 kilogram times cosine 30. And it's going in this direction, 2 kilogram, 30, and 3 kilogram, 20 meters per second cosine 30, and 3 kilogram times 20 sine 30. Plus impulse. Now your impulse is like this, F delta T. F delta T. That's in this direction. As a result of this one, they obtain new momentum, and the new momentum, again, it obtained 3 kilogram times VBX, 3 kilogram VBY. Very, very simple. You make a picture, and if you understand what is happening according to the impulse and momentum, and of course you have 4 unknown. You have 4 unknown that you have to obtain, that 4 unknown. Okay, so we have 2 particles. One is going with the velocity VA, 20 meters per second. One is coming in this direction, 20 meter per second. Mass of this one 3 kilogram, mass of this one 2 kilogram, and it collide. It collide, and we are interested to see what is the force, what is the velocity. What's the velocity? So you can say no problem. No problem. And the simplest way that you can do, and at least think about it, you can say I have some momentum, it's subject to some impulse, and obtain some momentum. I have some particle here, it's subject to some, it obtains momentum. All right. So you could have also put your coordinate system not x and y. You could. This is one way to do that. You could have simply said, I would like to use this one as x and this one as a y. Not a problem. Not a problem. You can use any coordinate system you have. If you use this coordinate system, maybe the life a little bit becomes easier to understand what's going on. Maybe easier. All right? And I will tell you why it is easier. Let's do that one. I come back to this one again. But you can do that. This one. I come back to this one, and I do this one as well. So, but let's go ahead and use that one. If you use that coordinate system, the life a little bit becomes easier. A little bit easier. Not that much. Don't expect that much. A little bit. So you can say, OK, no problem. What is my momentum? Well, this time, my particle A, and this is x. This is y. My particle S has momentum in this direction. That's momentum. That's 2 kilograms times 10 meters per second. And this angle is 30 degrees. That's your particle. This particle is subject to some momentum, some impulse. And the impulse is in this direction. You can say F delta T. F delta T. Impact. And we are assuming no friction. We are assuming no friction. If you have a friction, then that would be produce another momentum in the other direction. We assume collision is frictionless. But if you do have a friction, then you do have another impulse in this direction as a result of sliding or something like that. So, but here we assume frictionless. As a result of that one, this obtain new momentum in the x direction and the y direction. 2 kilograms times VBx, VAx, 2 kilograms VB, VA, y. Because you have to write in x and y. For the particle B, your momentum is in this direction. 3 kilograms times 20 meters per second at the angle of 30 degrees. Then it is subject to some impulse. Well, let me write it exactly underneath of that one. Then it is subject to the impulse, and that impulse is F delta T. As a result of that one, it obtained new momentum, and the new momentum you have to say M 3 kilogram VBx, 3 kilogram VBy. So the life a little bit becomes easier, a little bit easier. Compared to, there is no reason for the other one is not a problem too, but that means you have to think a little bit more. Still you have 4 unknown, which is the same as previous one. So recasting again, Newton's law says F is equal to d over dt of mv, change of momentum. Or F delta T is equal to change of momentum. You can make this one as a graphic. You can change this one graphic. This becomes mv2 minus mv1. You can bring this one to the other side of the equation. Then you can make a picture. Make a picture. That's my F delta T. That's my mv is equal momentum. F delta T momentum. F delta T momentum. That is this equation, which is Newton's law. That's Newton's law, except we multiply both sides of the equation by delta t, and so know as if we obtain the new equation. So picture is beautiful. You make a picture is beautiful. So now we go ahead and we say what's going on. So if you look at this picture, if you look at the first picture, what do you understand? If you look at the first picture, what do you understand? You have a bunch of vector. What do you understand from the first picture? What do you understand? What do you understand from this picture? What do you understand from this picture? Forget about the second one. What do you understand from the picture? Don't look at me. Think about the equation. What do you see? What do you see in the first picture? First picture. Forget about this one. Forget about this one. What do you understand from first picture? That's right. You have a vector in this direction. You have vector in this direction. You have vector in. This is 20 cosine 30. And this one is 20 sine 30. So now you can see this vector plus this vector must be equal to this vector. This vector plus nothing must be this vector. So that is a vector. So you can say 20 cosine 30 minus f delta t must be equal to 2vbx, 2vax. This one plus nothing must be equal to this vector. So you can see vby stays the same, so which is 10 meters per second. 10 meters per second. So this becomes 10. So you can see that from here, if you write it in the x direction, you can say that 20 cosine 30 minus f delta t must be equal to 2vbx, 2vax. In the y direction, for that picture, that becomes 10 plus nothing must be equal to 2vby, vay. So you can see vay is equal, you find one of the unknown. You still have 4 unknown. That's one of the unknown. So you can find vay is equal 5 meters per second. Still vax is unknown. Same thing for this picture. This vector plus this vector must be equal to this vector. So now you can say that becomes 3 times 20, 3 times 20, negative, opposite direction. F delta t in this direction must be equal to, in this direction, 3vbx. In the y direction, you do not have anything in the y direction for this picture. You do not have anything in the y direction for this picture. And so 0 plus 0 must be equal to 3vby. So therefore, you obtain velocity vby is equal to 0. Now, if you add these two equations together, you get rid of that f delta t. You get rid of that f delta t, and you get one equation but two unknown. That's called conservation of momentum in the x direction. So, but really, momentum in the x direction, momentum in the x direction is equal to momentum in the x direction and momentum in the x direction. So that's called conservation of momentum in the x direction, in the direction of applied force. So you can say momentum in the x direction, 20 cosine 30 minus 3 times 20, 3 times 20 is equal to 2vax plus 3vbx. That's called conservation of momentum. Momentum in the x direction, momentum in the x direction is equal to momentum in the x. So you get one equation that's called conservation of momentum. Conservation mode. So you end up with one equation and two unknown. And of course, f is delta t duration of the impact should be given to you. Whether you touch it slowly, you delta t should be given to you. Delta t is, it should be, and of course f, we do not know what is f also. So we cannot f. Even delta t is given to you, but we do not know what's f. So this is called conservation momentum. Conservation of momentum. We need one more equation. We need one more equation, and that one more equation should come that how this impact happened. How the impact happened. Is it the impact is elastic, or there are some material deformed there, or they stuck together, or something like that. So you have to say something about that process of the impact, how that impact happened, whether these two particles went together, or maybe they hug each other, then they got separated. So that is what we have to bring, the concept of coefficient of restitution. So we need one more equation, and somebody has to tell you what's the coefficient of restitution. And the coefficient of restitution is, and we are going to do the same thing for rigid body. When we go to the rigid body, we do the same thing. And we always ask in the qualifying exam for PhD student, when something dropped rigid body and how this thing happened. Right now we are talking about particle. There is no geometry. But we can do the same thing for it. So when you do have particle A and particle B is colliding here in the x direction, that's basically what happens in the x direction. Forget about in the y direction. Y direction is velocity is preserved if there is no friction. If there is no friction. If there is a friction, velocity is not preserved either. So velocity would be different. But if there is a frictionless, so when you do have two particles, and this is coming with the MVA, and this is coming, suppose, with the MVB, we always write in the positive direction. And collision happens. And when the collision happens, this is momentum before the impact. Before impact. Now the collision happens. The collision happens, and then there is some P delta T is happening here. So you do have momentum of particle A, MVA. Then you do have some collision, which we can call it P delta T. P delta T. Or we can say delta T1. The total one is delta T. And as a result, it obtained new momentum. We call it MVA prime. So the first thing they get together is like that. You see your friend, and all of a sudden you jump to his arm, and you start kissing, and I love you, all of those things. And then you see your friend has garlic, and she has a lunch, or he had a lunch for the lunch, and say, oh my God, it smells awful. And then say, see you. So that is a new momentum, MAV prime. And then you get some rejection, and that's a R delta T. Delta T number 2, and then you obtain final velocity, MVA final. So you start to hug each other, then you get some rejection, and then you get separated, and that's what happens during the impact. Same thing happens to particle B. Same thing happens to particle B, and from these two equations, we can define something that's called coefficient of restitution. How strongly you reject and how strongly you attract. That's called coefficient of restitution. So, and you have to do with the high-speed camera that you can say, okay, it took 2 seconds to get together, and then it takes 0.1 second to get goodbye. So you have to say how those things happens. So, and you have to do experiment. So you have to have a high-speed photography, and if something happens, and you see your friend, you jump and hug each other, maybe a couple of seconds you are kissing and hugging and all of those kind of things, but then you say, goodbye, and that is. So we can define coefficient of restitution, coefficient of restitution, as E defined as integration of R delta T or R delta T, delta T to 1, integration of P delta T. Or you can say P delta T to 1, P R delta T 2, that doesn't make any matter. So if you just go ahead and do this one, the coefficient of restitution is defined as E is equal to, for particle A, MA VA final minus MA V prime, that's a intermediate velocity that you obtain, divide by MA V prime minus MA VA. And of course, MA cancel each other, so they can say VA minus V prime A divided by V prime A minus VA. What's the V prime A? V prime A is this VA final. We better put final here. V prime A is an intermediate. When you hug each other, you have some velocity together. So because you have hugged each other as if you have one body. So that is called V prime A. You can do the same thing for particle B. And for particle B, again, you do have some MBVB. Then you do have some force is the same, and you do have action and reaction, P delta T. And as a result of that one, it obtained new intermediate velocity, MBV prime B. Then rejection happened. Then you have rejection. So it has intermediate velocity, MBV prime B. Then you do have some rejection, R delta T. Then you do obtain final velocity, MBVB final. So you can go the same thing. You can find what's R delta T to P delta T. And if you do that, the coefficient of restitution for this case becomes equal VB final minus V prime, which V prime B is the same as V prime A. It's the same thing. That is intermediate velocity. So V prime B divide by V prime B minus VB. And of course, we know that V prime B is the same as V prime A. If you eliminate V prime A and V prime B from these two equations, you get another equation. So elimination, V prime B is the same as V prime A. If you eliminate V prime B and V prime A from these two equations, you get something that's called coefficient of restitution, and that is E is equal to VB minus VA final, VA minus VB initial. And of course, this is in the line of the impact. You do this one in the x direction. So for our previous problem, that we end up with one equation, two unknown, the coefficient of restitution should be given to you. And the coefficient of restitution, if E is equal to 0, that means a plastic impact. That means that these two bodies, they got together because VB becomes equal to VA. final, that means together. So if E is equal to 0, that means plastic impact. Plastic impact. And that means that if you just go ahead and do this mathematics and eliminate, you end up with this final equation. That final equation tells you if E is equal to 0, VA final is equal to VB final. And E is equal to 1. If E is equal to 1, that's called elastic impact. Elastic impact. So your coefficient of restitution is some number between 0 and 1. Some number between 0 and 1. So for the previous problem, if I tell you the coefficient of restitution is equal to, for this problem, that this is coming with the velocity here, 20, what was that? I don't remember what it said, 20 cosine 30? Yeah, 20 cosine 30. And this is coming with the velocity of the 10. What was the velocity of that B, we said? What's the velocity? 30? Was 30 meter per second? OK, this was 20 meter per second. So if we give you the coefficient of restitution, then you can say, no problem. We already have one equation for conservation of momentum that basically 2 kilogram times 20 cosine 30 minus 3 kilogram times 30 must be equal to 2 kilogram VBX, VAX, plus 3 kilogram VBX. That's called conservation moment. That's my first equation. Now I have to give you another one, which is basically, we just go ahead based on coefficient of restitution. And if we do the coefficient of restitution, and we say the coefficient of restitution is 0.2, then you can say coefficient of restitution E is equal to 0.2 for this problem, is equal to VBX final minus VAX final is equal to VAX is equal to 20 cosine 30 minus VBX, that is minus 30. So now you get another equation, and from this equation and this equation, you have two equations, two unknown, and then you can solve the problem. You can do the same thing in the capital X and Y direction. Same thing. So change of coordinate system. So I'm not going to do that one. You can do it yourself. Let's do another problem. Same concept. Let's say that you do have something here, a bar, and this length is 60 meter, and this length is 20 meter, and this bar is sitting, and let's assume this bar is massless. Later on, I will solve a problem that bar is not massless. Let's say that we have this one massless. Massless. And this particle is coming down with a velocity of 20 meters per second down, and the weight of this one is 2 kilograms. And this mass is sitting here. It's sitting here. And then you put some, drop this one. What happens to this ball? What happens to the ball? It is going to fly. Have you done that one before? Maybe you were doing seesaw. Have you done the seesaw? Your mom took you to a park, and you do the seesaw, and all of a sudden your mom hits you, and then you jump. Have you done? Has happened to you? Seesaw? Question? You have a question? You have no question? You sure? You have a question? What's the question? Which one? What? It should be given to you. It should be given to you. It is given to you that somebody during the high-speed photography, he finding out what is happening during that impact, what is the duration of impact, was it this one, then based on that one, they can go ahead and calculate basically what's the coefficient of restitution. So E should be given to you. That depends that if you just have a collision which is completely plastic, then you will get hugging and they don't get separated. But if it is elastic, you get completely separated, no deformation. And in between, E should be given to you. OK, so, and the question is that if this mass is 3 kilogram, how far does it go up? How far does it go up? How do you go ahead and solve this problem? How do you go ahead and solve this problem? And let's say that this one completely stick to this one. Maybe the collision is plastic. Maybe you have a piece of mud, and then you throw that one and stick to that piece, and then as a result of that one, then collision is completely plastic. Collision, complete plastic. So that this piece, let's make assumption, we can say is rebounding too. But then you have to bring something else and so forth. We haven't talked about rigid body yet. So the question is that, let's say that collision is completely plastic. That means that the piece get together. The piece get put together. Collision is plastic. So how do you go ahead and solve this problem? How do you go ahead and solve this problem? And what did I say? What did I say? You make a picture. You have to make a picture. So you can say, OK, what happens to this situation? And generally, we neglect gravity. Why we neglect gravity? Generally, we neglect gravity. Why do we neglect gravity during the impact? If you do have two balls that coming here and hitting each other, or you have, if this eraser comes from here and I dropped it here, we generally forget mg. Why? We generally forget mg for the impulse. We don't bring it to the calculation mg. Can you tell me why? Huh? The velocity. Let's get at that end. Yeah, not you. Yeah. That's right. Mg delta t becomes very small. Mg delta. F is big. If somebody comes and slap your face, then you really feel huge force. The delta t is small, force is huge. Delta t big, force. So mg delta t is almost zero. We never bring mg delta t to the picture of analysis. Impact is important. Force of impact is huge. All right, so what happens to this problem? What happens to this problem? We don't have that much time. So this particle is coming down with mv. This particle is subject to some b delta t or f delta t. And as a result of that one, obtain new momentum, m a v a final. Stick to that part, but the part may obtain some velocity. what happens to the bar? What happens to the bar? The bar is subjected to the F delta T. F delta T. As a result of that one, and assuming no mass. Otherwise, your problem is completely different situation. And then you do have some reaction, AX delta T, AY delta T. And as a result of this one, it puts some force against this one, and maybe some force, you can say F2 delta T. And that's for that bar. And to the particle itself, you do have F2 delta T. So you have three pictures. So then you do have this bar, this mass. Well, maybe I should put at the end so you can see I'm talking at this point. At the beginning is no momentum, nothing. Then you have F2 delta T, action and reaction. As a result of that one, obtain new momentum, MBVB. So if you make a picture, the life becomes a little bit comfortable to see what's going on. So you slam on this one, and as a result, you have some momentum. You have some F delta T, and you could have some rebound, but we said that there is no rebound. There's a stuck over there. So whatever the direction of that one is going to be, we will go with that. So that's one picture. To the bar, action and reaction. There is no momentum or angular momentum for because we assume it's massless. Later on, we solve this problem when the seesaw has a mass as well, and then you go. And as a result of that one, it produces some force against that particle, and action and reaction to that one is produce some momentum to this. So from this picture, can we go ahead and find what's the velocity of the B? How fast this ball is going to fly? Can we go ahead and find velocity of point B? How do we do that? How do we do that? If you look at this picture, how do we do that? All of these things. Yes?
So you can relate the forces using the lever arms.
Yeah. But what's the best way? I'm not interested to find forces. I'm not interested to find forces here. OK? I'm not interested to find forces. So if you put all of this picture together, so you put this force with this force together, it eliminates it. And I superpose all of this picture together. I superpose all of the picture together. And I superpose everything together, so I get rid of it, OK? Whatever I can get rid of it by superposition. It's like you can write equation and you can put them together. So if you put this picture, add to this picture, and add to this picture, what is the final thing would be left over? Well, the final thing would be left over. This and this get eliminated. So the only thing that's left over is MA VA. AX delta T and AY delta T stays there. That stays there. AX delta T, AY delta T stays there. And if I put this picture with this picture, it also get eliminated. The only thing that's left over is MA VA final and MB VB final. MA VA final. The only thing that's left over is, if I put this one, MA VA final, MB VB final. So it's like that you are adding the right-hand side of all of this equation, together. You add all of the left-hand side of all of this equation together, and you are adding the equation. I make a little bit shortcut. So now you can see that this distance, that's become angular momentum. In this case, it becomes conservation of angular momentum. Rather than linear momentum, you are multiplying this one by this distance, and this one by this distance. That becomes conservation of angular momentum, not linear momentum. Conservation of angular momentum. So in this case, there is nothing wrong to write all of this equation again. But if you superpose all of those pictures, then you come with this picture. MAVA is equal MAVA final, MBVV final. So therefore, you can say MAVA times this distance, 20 meters, is equal MAVA final plus MBVB final times 60 meters. You have one equation, two unknown, but we said they are stuck together. That means that the velocity of this one must be equal to, they are seesawing. So the velocity, if this is going down, this is going up. So therefore, we are saying that we have to have one more equation. So you can say that, well, you need a coefficient of restitution again for the point B, and that it gets separated. For point A, it's stuck together, so that's not a problem. But you need a coefficient of restitution. Why don't we continue this one next time? But next time we start rigid body motion. Rigid body motion.